Hello, welcome to Chapter 7, homework questions 73 to 78. Question 73. The U.S. Census Bureau takes a census every 10 years. The population in 2000 was estimated at 281.4 million people. A model created at the time predicted that the population grew at about 2% per year. First question, how many people would the Census Bureau have expected to count in the year 2005 census? So we could really set this up a couple different ways, as you guys know. We could use a table, but we really want to know a couple things. We could also use an equation. Because this is going to grow at a rate of 2% per year, we need two values. We need the initial, which is 281.4 million people. And then we also need the multiplier, but it tells us it grows at 2% per year. So that's 1.02. Remember, 2% is added on to the 100%. And then we have our equation. So as I said, you could create a table potentially, or if you write the equation, you can answer the question pretty quickly. Y is equal to 281.4, but remember that's million times 1.02 raised to what power? Well, if the initial population was in 2000, this is going to be at time 0. So in 2005, that would represent time 5. We're not going to actually plug in the year 2000 or the year 2005. You always want to start with your initial, which in this case was 2000, or at time 0. So we're going to use 5 as our exponent. And then when we plug this in, let's see what we get. And I got a value of 310, and it looks like they're rounding to the nearest tenth, so 310.7 million people in 2005. And so make sure you write that out and answer that question. On part B, if the Census Bureau had conducted a count in 2010, how many people would it have expected to count? So once again, we're still trying to answer the question is, it's 2000, but in 2010, how many people is the expected count? So we're going to plug in the time in just a second. So we got 281.4 times 1.02 raised to what power? Well, once again, 2010 is 10 years from the initial value of 2000. So we would plug 10 in. Let's calculate that. And we get a value of 343.0 is what that would round to. So that means there's 343.0 million people is what is expected in the year 2010. And once again, make sure you answer the question using words, not just writing y equals. Part C, the actual 2000 census put the population at 309 million. What is the residual and what does it mean? Well, remember, when you find your residual, you're going to take the actual, which they said was 309, minus the predicted at 343. And we get a value of negative 34. So that negative 34 would be negative 34 million people. It's important that we include the word million on here because we're not writing out all the place values. So negative 34 million people. But what does that mean? Well, it looks like the population was predicted to be 343 million, but it's only 309. So at some point, this model is not a good model anymore because the population has slowed down. And so the negative 34 million people is the residual, but in terms of explaining what does it mean, it means the population growth has slowed. Question 74, what values of A and B that make each system of equation true? Solve each system, it says, as a kind of a hint there. Be sure to show your work or explain your thinking clearly. So in part A, we have 6 equals A times B to the 0. And then we also have 24 equals A times B squared. Well, as you're looking at this and trying to solve, no, we haven't solved systems like this before, but let's see if we can kind of work through it. The first thing is on the first equation, we have B raised to the 0 power. Well, what is B raised to the 0 power? What is anything besides 0 raised to the 0? And that is a value of 1. So what you find out is A times 1 is A, therefore we found the value of A. Well, now that we know A is 6, now we can use substitution to plug the 6 back in to the second equation. And now we can solve for that one. So it's being multiplied by B squared, so we can divide to isolate the B squared. And then how do we undo a square? What's the inverse of that? and that would be the square root. Or you could just ask yourself, what times itself gives you 4. And so there we get a b value of 2. Now you might notice in the book that it only gives a equals 6 and b equals 2. But I challenge you to think about this a little bit more, because in reality, isn't there 2 numbers squared that could give you 4? Not only is 2 squared 4, but so is negative 2 squared. So we could potentially have a positive or a negative b on that one. All right, moving on to part B. B, we have 32 is equal to a times b squared. And then the other equation is 128 equals a times b cubed. So this one's a little different. We don't have that b raised to the 0, anything raised to the 0 here. So maybe a little bit more challenging to think about. One thing we could do is solve for a in the first equation by dividing by b squared. So a would be equal to 32 divided by b squared. Could we then replace the a in the second equation with 32 over b squared times b to the third, and that's over 1. Let's see what happens if we do this. Let's see, we get 32 times b cubed over b squared. We can simplify that because you could subtract your exponents or expand it out and see that this would give us 32b. Remember, b cubed is b times b times b over b squared. So those two equal 1, and then you're just left with 1b. And now we can divide by 32. And it looks like b would be 4. And so now that we know what b is, we can take b and plug it back into one of the original equations. I'll go with the first one here. And we have 32 is equal to a times 4 squared, or 32 is equal to 16a. Divide by 16, and we get an a value of 2. So we have a equals 2, and b equals 4. Now, that might not be the only way, and I'm sure it's not the only way to solve it. That was just kind of the way I was thinking. You could potentially do some guessing and checking as well. And there are other ways to look at that. So if you got the right answers, you want to show your teacher, that's fine. And they can check to see that you did it correctly. Question 75. Jack and Jill were working on simplifying the expression at the right, but they were having some trouble. Then Jill had an idea. Can't we separate the parts, she said. That way it might be easier to tell what we can simplify. She rewrote the expression as shown at the right. Okay, said Jack, now we can rewrite each of the parts with negative exponents and simplify. Let's help Jack and Jill finish simplifying their expression. So you can see their expression is 3 times x squared times 1 over x to the negative 1 times y to the negative 3 times 1 over y squared. Now let's go back and at least look at where that came from. So here's their original. All they did is separate each of the parts out. So you have the 3 separated, you see the x squared, the y squared is in the denominator, so it's rewritten with the y squared in the denominator on this one. And then the negative 3's are also just separated out. You have one on top here, which is the y to the negative third, and then you have one on bottom, so it has to be 1 over x to the negative 1. So Jill just separated them out. Now that they're separated out, can we rewrite each of the parts with negative exponents and simplify it? So now let's take anything that's raised to the negative power and simplify it. So remember, if it's raised to the negative, we do the reciprocal of this value. So it's 1 over x being the base of x, so that's x raised to the first power. So the reciprocal of 1 over x is x. Then you have y. What's the reciprocal of y? That's 1 over y, and then it's raised to the positive 3. And then the 1 over y squared, it's not a negative exponent, so you don't have to worry about it. And now let's continue to simplify. So these first 3 are all over 1. And so this is 3 times x squared times x over y cubed times y squared. And now we can combine the exponents with the bases of x by adding. So 2 plus 1 is 3. And then on the bottom you have y to the third, y to the second. 3 plus 2 is 5. So your final answer is 3x cubed divided by y to the fifth. So now can we take that idea that Jack and Jill had and use it to rewrite and simplify part B? All right, well, let's see. So let's write them out. M squared, that stays. You have p to the first, that stays, times q to the negative 1. So we're going to rewrite q to the negative 1. Times, now all of these in the denominator are 1 over. So it's 1 over 4 times 1 over m to the negative second times 1 over p times 1 over q to the third. So we just separated it all out. Now, anything raised with the negative, we're going to do the reciprocal. So we have m squared, p to the first, all those are fine. And then q to the negative 1 is 1 over q, and then now it's to the first power. Times 1/4, that one's fine, times m to the negative second. So 1 over m is m, and then now it's squared. Times 1 over p, that's fine. And then the last one, 1 over q to the third is fine. So anything that doesn't have a denominator has a denominator of 1. Multiply all your numerators, m squared times p, and then you get times 1 times m squared, and then more 1s. On the bottom you have 1 times q times 4 times 1 times p times q cubed. Now simplify. You have p times m. I'm going to rewrite those. I'm going to do m first. M to the second times n to the second is m to the fourth times p divided by, you want to put your coefficient first, which is the 4. And then we have p times q to the fourth power. Now the last thing that you can possibly do on this one, since you have a p in the numerator and denominator, they're both to the first power. P divided by p is 1. So it looks like our final answer is m to the fourth over 4q to the fourth power. Question 76. A particular sequence can be represented by t of n equals 2 times 3 raised to the nth power. What are t of 0, t of 1, t of 2, and t of 3? So in part A, we can find each of these values by plugging in 0 into the sequence 2 times 3 raised to the 0 power, and that would be 2 times 1, which is 2. So t to the 0 is 2. T to the first, 2 times 3 raised to the first power is 2 times 3. And so that will be 6. And you can continue this. Another way you could do it instead of doing all this work is if you understand the equation, you have n and t of n. So you can actually set up a table. If you plug in 0, you get 2. If you plug in 1, you get 6, because 2 is your initial, and then your multiplier is by 3. So you could actually multiply by 3 and get these answers a little quicker than plugging them into the equation. But obviously, either way is perfectly fine. So multiply by 3 one more time here, and we get 54. But even if you're using the table, you still need to make sure that you're writing the answers. So just because I have that, but I also need to say, okay, well, t of 2 is 18, and t of 3 is 54. So don't forget, just because you did the table, you still have to answer the question that is being asked. B, graph this sequence, what is the domain? So I went ahead and, just make it easier, went ahead and pulled the picture from the answer key so you can see the sequence. This represents n is your term number, and so this would represent n, and then this would be t of n. So at term 0, you're at 2. At term 1, this is 6. Term 2, you're at 18. And then term 3, you're at 54. It's a discrete graph because it's a sequence. But it also says what is the domain. So we want to make sure that we write the domain down. Remember, with a sequence, your domain is your term number. Well, the smallest value that you can have for your term number is 1. And so your domain is all those values. Now, someone might say, well, why did we plot this point? Well, because it told us to. In terms of it, the t of 0 up here, that's that initial. But if we actually have a sequence, we shouldn't include that. Even though it does say graph this sequence, I just noticed that it does include that point. So I would say we shouldn't include that point because it's not part of the sequence. It does on the answer key, but remember, t of 0 is not part of that sequence. It starts at term 1 and goes from there. So our domain would be our natural numbers, which is 1, 2, 3, 4, 5, or you could say whole numbers excluding 0. You could say your non-negative integers. So there's a couple different ways we could write that, but I'm just going to say natural numbers because those are our counting numbers, and that's what our domain represents. Now on part C, it says on the same set of axes, graph the function f of x equals 2 times 3 raised to the x power. Well, that's different because we can plug in our domain as all real numbers on C. It doesn't ask us to write this, but it's important to know that all real numbers, because now we can plug in anything. So that zero value is included, and all these other ones in between these values are included. So it's not a discrete graph, it's a continuous graph. So if I go ahead and graph it on the same one here, then it's going to look like this. It's still going to have those points, but these points will all be connected, and then we'll have an arrow here and an arrow here. And remember, this graph gets close to this x-axis, but it's never going to touch. That has that asymptote at y equals 0. Okay, so this is actually graph f of x, if it's written as a continuous graph. And then lastly, on part D, how are the two graphs similar? How are they different? We kind of answered that a little bit right there. They definitely have the same shape, but the sequence is discrete and the function is continuous. And so you can see for D what I wrote down. The similarity is same shape. The difference there is, as I said before, t of n is discrete and f of x is continuous. Question 77. Solve the system of equations at right algebraically. So it's all the way over here. We just need to solve it. Pick, once again, whatever method you want. I have 2x minus 3y equals 12, and I'm just rewriting it. I am going to rewrite, though, it has y plus x. I'm going to switch the order and put the x plus y first. So you have your substitution or elimination. Either one of these two variables you could solve for really easily without getting fractions by just subtracting the other one. So you could use substitution pretty easily, but since I moved my x and y in the order that it lines up with the first equation, it's also now set up for elimination. So you make the decision, doesn't matter, it'll work either way. I'm going to go ahead and use elimination. I'm going to go ahead and eliminate the y by multiplying by 3. So this will give me 3x plus 3y equals negative 27, and then I'm going to rewrite the first equation over again. If you eliminated the x, you'd have to multiply the bottom equation by negative 2 if you wanted to eliminate the 2x in the first one. So either way is fine. We're going to add these two equations. 5x is equal to, and so now you're going to have the y's canceled, the 3y's equals negative 15. Divide by 5, and x is equal to negative 3. And now you're going to plug that back into one of your two equations. I'm going to go ahead and plug it into the second one here. So negative 3 plus y equals negative 9. Add 3 to both sides. Y is equal to negative 6. We'll go ahead and write this as an ordered pair. That is the intersection of the two lines, which is the solution to the system. And remember, if you do want to check this, it doesn't say to, but if you do want to check, you can always plug it back into both equations and make sure it works. And so I went ahead and showed the check just to show you what it would look like, but you do have to plug it into both. Last question, question 78. Each team in Ms. Zielinski's class cut a circular disc from cardboard file folders. They could cut the disc any size they chose. The weight and radius were recorded. The information is shown in the table below. Since students chose the radius, consider radius the independent variable. So there's the information with the radius, and that represents the independent variable, and the weight is the dependent. Part A, make a scatter plot for the data and sketch it on your paper. Describe the association between the weight and the radius. So you don't need a graphing calculator for this part. You are just making a scatter plot from the data. Now, you're eventually going to have to use the graphing calculator to do some of the rest, but for now, this part right here represents the scatter plot. Obviously, it's a picture pulled from the graphing calculator, but yours should look something like that, where the radius is your independent and the weight is your dependent. Now, describe the association between the weight and the radius. So you can see on the scatter plot that this is going to be more of a non-linear example. So you can kind of see that curve there that we'll eventually get there. So when we describe the association, the weight is very strongly positive associated with the radius, but in a non-linear manner. Okay, so once again, this is going to be looking at non-linear on this particular example. So for the answer to describe the association, I just wrote that below. Now the next part on B, it says the weight of the cardboard disc depends on its area. What kind of equation do you suggest to model this data? So we know it's some type of curve, but if you remember about area of a circle, it's equal to pi r squared. So what kind of model would that represent? Well, dealing with squared, that would be a quadratic model. So we could do a quadratic regression. At least try a quadratic regression to see if it's a good model for the data. And then on the next part, model the data with a regression equation. Does the y-intercept of your model make sense in this context? So you would definitely have to use the calculator at this point or something to calculate what that would be. Going to use R for the radius and W for the weight. So for part C, the line that you would calculate from your calculator would be W, which is the weight, is equal to 0.056 times the radius raised to 2.01. And once again, that would be something that you would find from the calculator. So does the y-intercept of this model make sense in context? So as you're looking at this, that y-intercept would be what? And so the y-intercept would actually represent, if you plugged 0 in for, in this case, your R value, you would get 0 back for the weight. And that does make sense, because if you have a disk with 0 radius, then it's obviously not going to weigh anything either. So make sure you include some type of description for that. What do you predict a 7-centimeter disc will weigh? Use appropriate precision in your answer. I also went ahead and showed you the line, the quadratic regression. I went ahead and graphed that as well so you could see how it fit the data once we did that. But now, kind of moving on to D, now we're trying to predict what a 7-centimeter disc would weigh. Well, that represents the radius, so plug that into your equation that you found, 0.056, and then 7 centimeters is the radius, and we'll raise that to the 2.01. So what would your weight be? Plug that in your equation, see what you get. And if you look at the weights, all the weights were rounded to the nearest tenth. So this one is 2.79, which means we're going to round to 2.8, and that represents grams. So what do we predict a 7-centimeter disc would weigh? We predict that it will weigh 2.8 grams, and we want to make sure we write that out as well. And so that's what I'm talking about, making sure you write out, answer that question. And that is it for these questions. See you in the next video.